Now we'll take a look at how we apply some of those higher order derivative concepts here when we look at velocity and acceleration. So I'm going to look at 3 slides here, looking at average velocity, then instantaneous velocity, and then acceleration. So first example is one we've actually seen before, but just giving it a little bit more realistic nature. So we know that the average value or the average rate of change of a function is defined by this, basically this slope calculation, f of b minus f of a over b minus a. Well, we call that the average velocity when we're talking about an object's change in terms of its distance over time. So let's look at an example. Tommy leaves for TCU at 7 a.m. and he arrives at 1 p.m. So from 7 a.m. right to 1 p.m. he's covering 6 hours, right? He starts off at 14,300 miles and then takes him to 14,905 miles. So it says, what was Tommy's average velocity? So basically, when you look at A and B and that kind of stuff, you're looking at 2 different points here. You're looking at 7 a.m., right, and 14,300 as one data point, and you're looking at 1 p.m., right, 14,905 as your other. So really what we're doing is we're doing 14,905, kind of like the end of his trip there, minus 14,300 all over that 6-hour time period, and that's going to be his average velocity. So if we just get our calculator out and take a look, then we'll get his average speed. And so I got a really fast 100.83 miles an hour. So Tommy's flying. But you get the point. All right, let's look at instantaneous velocity. So you can start to see right away, if we're given a function, and usually the position function is defined using s, then we take the derivative of that, and that gives me velocity. So this particular example says bullets fired, right, and its distance is given by this 8 minus quantity 2 minus t to the third. So it says find the velocity exactly 0.75 seconds after the gun's fired. So the first connection we need to make is that in order to get velocity in general, I have to take the derivative of this s function. So v of t is going to be the derivative of 8, which is 0, right, minus, and then we have to get into, this is actually a little bit of a chain rule here, so 3, 2 minus t to the second power, times the derivative of 2 minus t, and that happens to be -1. Right, so now let's just kind of clean that up just a little bit. Right, the velocity here looks like that negative right here times the -1. Really, I could just make this positive 3, 2 minus t squared. Now that's the first part. To find the velocity at 0.75, that's basically just as simple as plugging in 0.75 to my derivative. Right, so again, probably going to need a calculator here, but let's just plug it in. And when we do, you can even take a minute and do it yourself. I got 4.6875, and then always be aware of units, right? So the distance here is meters, time is seconds, so that speed is 4.6875 meters per second. Okay, last piece of the puzzle is acceleration. So you notice 2 tick marks here, which means the second derivative. So acceleration is going to be the second derivative, velocity is going to be the first derivative. So big concept there. Find the acceleration of this bullet 1 second after the gun is fired. Well, let's go back for a second. The velocity we got, right, was 3 parentheses 2 minus t squared. So the acceleration then is going to be 3 times, then we're going to bring that 2 down, right? 2 minus t to the first times -1. So my acceleration here is going to be -6 times 2 minus t, and they would like me to plug in 1 for t at this point. So my acceleration at time 1 is going to be -6 times 2 minus 1, and that would just give me -6, and then the units here would be meters per second squared. Just a little introduction to velocity and acceleration. We're going to look at some more realistic problems in class, but at least this starts you off.